In this final lecture, we will first review the various properties of a nice Markov chain, which ensures steady-state behavior, and go over some of the notions in more details with some examples, providing some insights on how good an approximation we have when we use steady-state probabilities to characterize the behavior of a Markov chain which has run for a long time, but not an infinite amount of time. We will then consider a classical application of Markov chains, which has to do with the design of a phone system. This is a famous problem, which was posed, analyzed, and solved by a Danish engineer by the name of Erlang. It was more than 100 years ago, when phones just started to exist. But we will see that this methodology remains relevant to design similar systems in today's world. We will then make use of all what we have learned so far in order to calculate some interesting short-term behaviors of Markov chains having more than one recurrent classes. We will introduce the notion of absorbing states, and we will show how to calculate the probability of ending up in such a state, as well as related quantities, such as the expected time it takes to do so. As a classical example, we will look at a gambler continuously playing a simple game of chance, say a lottery, until he either accumulates a given amount of money or loses all his money. Both these states are absorbing. What are their corresponding probabilities? After this lecture, you will be able to answer such questions.
So we have reached the final lecture of this class, which will also conclude our study of discrete time, finite state space Markov chains. We will first review the steady-state behavior of Markov chains. Then, we are going to talk about a classical application of Markov chains to analyze the design of a phone system. And finally, we will see how we can calculate some interesting quantities that have to do with the behavior of Markov chains over a finite time horizon, as opposed to in the long run. So let us start. So let us first review the steady-state behavior of Markov chains. Consider again the following example. This chain has some recurrent states, some transient states, and a single recurrent class. So for example, state 9 is recurrent, state 3 is recurrent, state 5 is recurrent. And why are they recurrent? Because whenever you are in 9, no matter where you go, there is always a way to come back. Right? You can go to 3 and come back, or 5 and come back. And actually this is a recurrent class. And this is a recurrent class because all these recurrent states communicate between each other. What about the other states where they are not recurrent? So for example, state 1, once you're here, there is a possibility that you go there and you will never come back, so it cannot be recurrent, so it's transient. What about 4? 4 also has the possibility at one point to go there, and then from there it will never come back, so 4 is also transient. As for 2, no matter where he goes, well, he's going to reach or touch a transient state, so by definition it will be also transient. So they have 3 transient states and 3 recurrent states. Also, this recurrent class is not periodic, so it's aperiodic. And why is it not periodic? Well, here there is a simple way to tell. We have the existence of a self-transition probability, and that's enough to show that this recurrent class is not periodic. So this is one of the nicest possible Markov chains, in the sense that they have the following property. The probability that you find yourself at some particular state j at time n, when n is very large, converges to a steady-state value that we denote by pi of j. There are two aspects to this property. First, the limit exists, so the probability of stage j does not fluctuate. It settles to something in the long run. And furthermore, that probability is not affected by I. Now, if we don't know where the chain started, and we want to know the unconditional probability of being in stage j in the long run, when n is large, then either we are given an initial distribution over the states Or we can choose any initial distribution. For example, we can assume that all initial states are equally likely, or any other type of distributions. And then you can condition over all the initial states, use the total probability theorem, and you are going to get the same answer pi of j in the limit. Let's see how to do that. So this is the summation of all I. So you condition on that state I, so it's Rij of n times the initial probability distribution of your choosing. Right? So this is the total probability theorem. Now in the limit, when n goes to infinity, this goes to pi of j, independent of I. So you can take this expression in the limit and take it out of the summation, and then you have the summation of the probability of x0 equals 1. These are probabilities, so they sum to 1. So in the end, you have that converges to pi of j. So the conditional probability, given the initial state, is in the limit the same as the unconditional probability when n is large. And in that sense, it tells us that x of n and x of 0 are approximately independent. They become independent in the limit as n goes to infinity. So if the Markov chain has run for a long time and you are asked the question, where is the chain now? Then your answer should be, I don't know, it's random, but it's going to be in a particular j with that particular probability pi of j. So in that sense, the steady state probabilities are valuable information. So how do we compute them? Well, for transient states like these, they are 0. So pi of 1 is 0, pi of 2 is 0, and pi of 4 is 0. And why is that? Well, if your initial state were one of these states here, the probability of being in here is 0 no matter what. But even if you started here initially in one of these states, you might for a while fluctuate and turn around like that. But eventually, after a finite amount of time, you will go to that class and never come back to 1. So in the long run, the probability of finding yourself in state 1 will be 0. And this is the same for 2 and 4. Now, how do we calculate these? Well, for these states, in the recurrent class, we compute them by solving a linear system of equations, which are called the balance equation, these, together with an extra condition, the normalization equation, here, has to be satisfied because these are probabilities and they have to sum up to 1. And we have seen that the system of m plus 1 equation provide a unique solution to this kind of system for the recurrent class. So you would apply that to that recurrent class, and in that example you have 3 states, so you would choose m equals 3 for that example, and you would solve this system to get the pi j's. Now, what if we had multiple recurrent classes? Consider this chain. It is an expanded version of the previous one with additional states. Some of these are recurrent and one is transient. But now we have 2 recurrent classes. And that was our one class, so class 1. And now we have a second recurrent class, class 2. So what happens in the long run when you have situations like that? Well, in the long run, if you start from here, you're going to stay here. And in some sense, the study of that recurrent class is the same as the study of that recurrent class. And in order to find the steady state probabilities of these states, assuming that you started in one of these, will be exactly the same as before. So you would use the same system with m equals 3 here. Now, if you had started here instead, again, this is the recurrent class, and you have m equals 2 states here, and in order to find what is the steady state probabilities of these 2 states, you could use the same kind of result here, but you apply it with m equals 2 in isolation. So you just concentrate on that. If on the other hand, your Markov chain started from here, for example, for that specific example, you are guaranteed that at the next transition you end up here, and then you can do the same thing as before. We still know that this steady state probability of 8 will be 0 and 0 and 0 and 0. Now, what would happen if you started from here, from one of these states? Well, again, for a while you might travel throughout this system here, but eventually you're going to move away from that, and you will either go through a transition going into that recurrent class via this transition or via this transition. And once you are in there, essentially the chain will remain there, and so you do the same calculation as before. And if on the other hand you transition away from that class and arrived in this recurrent class, then you would apply the result that you had here. So in some sense, conditional on the fact that you left these states and you arrived there, in that conditional world you can isolate yourself and really solve the problem for that class, and the same from that class. Now, of course, this raises the question, if I start from here, how do I know whether I'm going to get here or here? Well, we don't know. It's random. So we will be interested in calculating the probabilities that eventually you end up here versus here. And this is something that we are going to do towards the end of today's lecture. As a warm-up, just to see how to use steady-state probabilities, let us look at our familiar example. This is a two-state Markov chain, and we did write down the complete balance equations for this chain and found the steady-state probabilities before. Notice that we can find these by using the trick which we introduced for birth and death processes. You cut the chain along this line and argue that the frequency of transition of this type has to be the same as the frequency of transition of this type. So if you have pi 1 here and pi 2 here, what it means is pi 1 times 0.5, which represent the frequency of these kind of transitions, has to be equals to pi 2 times 0.2, which is to this kind of transition, plus pi 1 plus pi 2, the normalization equation. And by solving this system of equation, you obtain the same thing as what we obtained before, which is the steady-state probabilities of state 1 and of state 2. Let us now try to calculate some related quantities. Suppose that you start at state 1 and you want to calculate this particular probability. So you start at state 1 and you want to know what is the probability that next time you will be in state 1, and 100 times step later you are still in state 1. Now, the conditional probabilities of two things happening is the conditional probability of the first one happening, x1 equals 1 given x0 equals 1, and given that the first one happens, the probability that the second one happen, x100 is 1 given x1 equals 1, x0 equals 1. So what is this? This first one is the transition probability from state 1 to state 1, p11. How about the second probability? Because of the Markov property, that information is irrelevant, and so that probability is R11 in 99 steps. Now 99 is possibly a big number, and so we approximate this quantity, and we are going to use the steady-state probability of state 1 for doing that. And that gives us an approximation, p11 times pi of 1, which then is 0.5 times 2 over 7. Now, how about this expression? Given that you start in state 1, what is the probability that at time step 100 you are in 1 and time step 101 you are in 2? By doing the same technique, it's the conditional probability of the first thing happening, and then given that thing happening, the probability that the second one happen. 1 equals 2 given x100 equals 1 and x0 equals 1. And again, here what we have is R11 of 100, and times, again, the Markov property tells us that we can forget about this one, and this is the probability transition from 1 to 2. pi 1, 2. And again here, if n equals 100 is large enough, we can approximate that by pi 1 times p1, 2. And this is then 2 over 7 times 0.5 again. Finally, let's calculate this third expression, where again we start at state 1, and now we are asking what is the probability that after time step 100 you are in 1, and 100 steps later you are again in 1. We use the same trick as before. There's probability that the first thing happen, and given that, the probability of the second one happen. Again, this is R11 of 100, and this one, for the same reason as before, we can forget this term. From 100 to 200 you have 100 time steps, R11 of 100, and 100 is big enough, so we're going to approximate both by the same values, and we get pi 1 square, which is 2 over 7 square. Now in this calculation, we assume that n equals 99 or n equals 100 were big enough so that the limit has taken effect. But how do we know that our approximation is good? In other words, is n equals 99 or 100 large enough? Well, this has something to do with a mixing timescale of our Markov chain, and by mixing timescale I mean how long does it take for the initial states to be forgotten. So how can you see that here? Well, you can first try simulation. So using any of your favorite software, you simulate and you calculate, and you look at as a function of n, and you draw R11 of n. At n equals 0, this is 1. N equals 1, then you have 5, etc. At 1, this is going to be P11, and P11 was 0.5, so already it's here. So initially it was here, here. And 2 over 7, so this is 0.5, 2 over 7 is here. And what we know is that when n goes to infinity, these things goes to 2 over 7. And if you simulate, you will see that it goes very fast. So here I'm just joining points, and you will see that at n equals 5 already you are very, very close to 2 over 7. So you have really an exponential decrease here. In fact, if you look at the simulation result and you look at n equals 5 already, here you have 2 correct decimal already, and for n equals 10 it's correct up to 5 decimals. Or if you do not want to have simulation but simply think in terms of order of magnitude, so here it would be another approach, would be like order of magnitude type of argument. And in order to do that, starting here, on average, how many trials or how many time steps would it take in order for you to observe such a transition here? Well, you use the geometric random variable, and this is the amount of time on average until you have success. And it is 1 over the probability here. So it takes on average 2 time steps to go from here to here. And to go from here to here, it takes on average 1 over 0.2, which is about 5 time steps. So as an order of magnitude, given you started here in state 1, after on average about 10 iterations, there will be some randomness. There is a high likely on average that you will go there and come here. And if you do n equals 100, which is 10 times that, in terms of order of magnitude, it looks like n is large enough. So that would be a back to the envelope calculation. Now this kind of calculation is useful in general, not just here. So for example, let's do it again. Assume that instead of 0.5 here, the probability that you had was 0.99, and maybe here instead of 0.8 it was 0.998. Now in order to observe such a transition, it will take on average, since this number here would become 0.001, it would take on average about 1000 time steps in order to observe one such transition. So if you look at time steps of that order, it will not be enough if your chain were of this type. After n equals 100, the likelihood would be that you will still be here, so the initial state or the initial condition would matter still. So it would take about 1000 to get there, and then here it would have 0.002. That means that on average from here it would take about 500 iterations before you observe that for the first time. So the same order of magnitude. So in order to get enough randomness here, a good rule would be to multiply this 1000 by 10. So maybe with n equals 10,000 you would feel confident enough in that specific case in order to use this kind of approximation that we have used here. And finally, for those interested, you can study that by theory. And here there is an anti-field that tries to study how fast a Markov chain converges to steady state, and the so-called mixing time. And it turns out that for these Markov chain, you can say that the convergence, or the rate of convergence, is of the order c at the power n, where c is a number that is between 0 and 1. And the closer c is to 1, the slower the convergence is. And the closer c is to 0, the faster the convergence is. And for example, here for our initial case, the c was 0.3. So that was the first case. For the second chain, with this kind of probability, 0.99 and 0.998, the c would be 0.997. In this video, we will consider a classical application of Markov chains, which has to do with the design of a phone system. This is a classical problem which was posed, analyzed, and solved by a Danish engineer by the name of Erlang. It was more than 100 years ago when phones just started to exist, but the technique remains relevant today to design systems of a similar nature. As for Erlang, he was trying to figure out how to design the capacity of a phone system. That is, how many lines should we set up for a group of people, say in a village, to be able to communicate to the outside world. So here is a cartoon of the problem, where these are the phone lines, and we need to decide how many of these lines to set up, let's say B. How to do that? Well, we don't want B to be too large, much more than needed, because too many lines would be expensive. On the other hand, we want to have enough lines so that if a reasonable number of people place phone calls during the same period, they will be able to talk and not get busy signals. So if B is 10 and 15 people want to talk at the same time, then 5 would get a busy signal, and that's probably not what you want as an acceptable level of service. So we would like B to be just large enough so that there is a high probability that no one is going to get a busy signal. So how do we go about modeling a situation like this? Well, we need two pieces of information. One describing how phone calls get initiated, and once a phone call gets started, how long does it take until it ends? We're going to make some very simple but somewhat plausible assumptions. We will assume that phone calls originate as a Poisson process. We will assume that out of that population there is no coordination. At completely random times, people pick up their phone independently of each other's. Also, there is nothing special about various times, and different times are independent. So a Poisson model is a reasonable way of modeling a situation under these assumptions. We also assume that the rate lambda is known or has been estimated. Now, it might be the case that during the night the rate would be different than during the day. In that case, you would design the system to meet the largest rate of the two. For the phone calls themselves, we are going to assume that the duration of a phone call is a random variable that has an exponential distribution with a certain parameter mu. So 1 over mu is the mean duration of a phone call. Duration of phone calls are independent between each other. So here again, we assume that the parameter mu has been estimated. For example, the mean duration 1 over mu could be 3 minutes. Now, is the exponential assumption a good assumption? So here is the PDF of an exponential random variable with parameter 1 over 3. That means that the mean duration is about 3 minutes here. So if you look at this PDF, it means that most phone calls will be kind of short. There is going to be a fraction of phone calls that are going to be larger, and then a very small fraction of phone calls that are going to be even larger. So it sounds reasonable. However, it's not exactly realistic in some situations. Typically, phone calls that last a very short time are not that common, as opposed to what an exponential distribution would indicate here. So some other distribution might be better, like this one, for example, here, where during a very small period of time, the weight corresponding to this very short period of time are kind of small as well. There are many distributions of this type. I've just provided here one simple example. This one is the Erlang of parameter 2 and 2/3. What it means is that it is the sum of two independent exponential random variables and each one of them of parameter 2/3. So the mean duration associated with this distribution is also 3 minutes. So this might fit better some practical situation, but here we will keep the simple assumption associated with an exponential distribution. Alright, so let's try now to come up with a model so that we can decide how many lines B do we want to set up. The Poisson process runs in continuous time, and call durations being exponential random variables are also continuous random variables. So it seems that we are in a continuous time universe. Here is the cartoon of the evolution of the system. So here I have in blue when phone calls get initiated. So this is called 1, a second one, a third, a fourth, and a fifth one. And also I have represented here the duration of the call. So call 1 lasted that long, call 2 lasted long until here, 3 up to here, 4 here, etc. So when you look at this kind of system in that way, and you run through time in a continuous manner, and here you have 0 line busy, you have 1 line used, 0, 1, then 2 become busy, 3, 2, 1, and 0, and so on and so forth. Also note that if I look at that system at any time t, because of our assumptions of a Poisson process and an exponential duration for phone calls, and the memoryless property associated with these processes, it means that the past really has no information about the future, and so in some sense a Markov property is valid. So it looks like a continuous time Markov process would be needed here. And this is indeed an option. But we have not studied those in this class, so we will discretize time instead and work with a Markov chain. We are discretizing time in a familiar way, the way we did it when we studied the Poisson process. We are going to take the time axis and split it into little discrete time slots, each of duration delta. And delta is supposed to be a very, very small number. So now under this discretization, by the definition of the Poisson process, the probability that we'll see one arrival during any time slots of duration delta will be lambda times delta. Also, if at any time, like here, we have one simple call active, the probability that this call will end during any future time slot of duration delta is mu delta, like here. Indeed, as we have seen in Unit 9, an exponential random variable can be thought of as representing the time until the first arrival of a Poisson process with rate mu. What if you have I busy calls at the same time? Then the probability of having one call ending in a time slot of duration delta will be I mu delta. Like for example here, this one would correspond to something as 2 mu delta. Indeed, each of the Poisson processes associated with these calls with rate mu can be combined into a merge Poisson process of rate I times mu, and the call completion will correspond to the time until the first arrival of this merge Poisson process. For example, if I go back here in my situation here at time t, there were still 3 phone calls active, and I represent here the call number 2, call number 3, and call number 4, and their remaining duration. And if you look at these and you combine these 3 associated Poisson process into one, you get a merge Poisson process. And if you look now at the time arrival of the first event, which would correspond to here, it would be an exponential random variable. The duration here would correspond to an exponential random variable of parameter 3 mu. So in that case, if you go back to that representation here, the probability of a departure would be 3 times mu times delta. Okay, so let us continue with our discrete time approximation of our system. Again, we have the village, the lines, the b that we would like to decide. We have discretized the time steps. We have made some approximation, and we know that during any of these time slots here, the probability that you would get a new call is about lambda times delta. Lambda is the rate of the Poisson process. And given that you have I calls, the probability that one of these calls ends will be I times mu times delta. Okay, if we want to propose a Markov chain mol for this system, we need to specify the states and the transition probabilities. What are the states of the system? If you look at the system at any particular time, the minimum relevant information to collect would be the number of busy lines. Something like these 2 lines are busy, or all of them are busy, or none of them are used. Now, because of our assumptions, again, about the Poisson process arrivals and exponential duration of calls, and their memoryless property, that information is enough to fully describe the state of our system in such a way that we get a Markov chain. So the states are numbers from 0 to b. 0 corresponds to a state in which all the phone lines are free, no one is talking. B corresponds to a case where all the phone lines are busy, and then you've got states in between. Now let us look at the transition probabilities. Suppose that right now you are in that state. What can happen next? Well, a new phone call gets placed, in which case the state moves up by 1, or an existing call terminates, in which case the state goes down by 1, or none of the two happens, in which case the state stays the same. Well, it is also possible that a phone call gets terminated and a new phone call gets placed in the same time period. But when the duration of the time slots are very, very small, the delta here, this event is going to have a negligible probability, order of delta squared. So we ignore it. As we ignore the fact that more than one new call can happen, or more than one call can be terminated during a given slot. So what is the probability of an upward transition? That's the probability that the Poisson process has an arrival during the slots of duration delta. And as we have seen, this is lambda times delta. So each one of these upward transition has the same probability of lambda times delta. How about phone call terminations? If we have I phone calls that are currently active, the probability that one of them terminates becomes I mu delta. So here it would be mu delta, and here b mu delta. Now let us analyze this chain. It has the birth and death form that we discussed in the previous lecture. So instead of writing down the balance equation in a general form, we think in terms of frequency of transitions across some particular cut in this diagram. So for example here. The frequency with which transition of this kind happen or are observed has to be the same as the frequency of transition of this kind. The frequency of transition of this type will be, if you look at pi I here and pi of I minus 1 here, this transition here will happen with pi I times I mu delta. And the transition of this type here will be pi I minus 1 times lambda equals delta. And the frequency of these transitions have to be the same as the frequency of these transitions. So we have that equals that. And then we can cancel the delta in both. And we are left with this equation here. So this equation expresses pi of I in terms of pi of I minus 1. So if we knew pi of 0, then we can calculate pi of 1, and then in turns calculate pi of 2, and so on and so forth. And the general formula that comes out of this, after some algebra, is given by this expression, which involves pi of 0. Now, what is pi 0? Well, we can find it by using the normalization equation, the summation of pi I equals 1. You use this normalization, replace each pi I by their quantities as a function of pi 0, and then we obtain this equation for pi 0. So here again, we use that normalization, we replaced pi I by their value, we sum to 1, and we obtain pi of 0. And then in turn, from this pi of 0, you can replace the pi of 0 in pi of I, and you obtain a pi of I as a function of b, lambda, and mu. So if we know b and lambda and mu, we can set up this Markov chain, and we can calculate pi 0 and then pi of I for all i's. We can then answer a question like this. After the chain has run for a long time, how likely is it that at any given random time you will find the system with I busy line? Well, it will be pi of I. And also we can interpret these steady state probabilities as frequencies. So once I found pi of I, it also tells me what fraction of the time I will have I busy lines. And you can answer that question for every possible I. Now, we were initially interested in the probability that the anti-system is busy at any point in time. In other words, in that state here. So if a new phone call gets placed, it is going to find the system in a random state. That random state is described in steady state by the probability pi i's. And the probability that the anti-system is busy is going to be given by pi of b. And this is the probability that we would like to be small in a well-engineered system. So again, given lambda, mu, the design question is to find b so that this probability is small. Could we figure out a good value for b by doing a back-of-the-envelope calculation? Well, let's suppose that lambda is 30 calls per minute. And let's assume that mu is 1/3, so that the mean duration is 3 minutes. So on average, a call lasts for 3 minutes, and you get 30 calls on average per minute. Then how many calls would be active on the average? If a call lasted exactly 1 minute, then at any time you would have 30 calls being active. Now a call lasts on the average for 3 minutes, so by thinking in terms of averages, you would expect that at any time there would be about 90 calls that are active, 3 times 30. And if 90 calls are active on the average, you could say, okay, I'm going to set up my b to be 90. But that's not very good, because if the average number of phone calls that want to happen is on the average 90, sometimes you're going to have 85 and sometimes you'll get 95. And to be sure that the phone calls will go through, you probably want to choose your B to be a number a little larger than 90. How much larger than 90? Well, this is a question that you can answer numerically. By looking at these formulas, if you decide that your acceptable level of service pi of b has to be less than 1%, then you will find that the b that you need to design is to be at least 106. So you actually need some margin to protect against the fluctuation if suddenly, by chance, more people want to talk than on an average day. And if you want to have a good guarantee that an incoming person will have a very small probability of finding a busy system, here 1%, then you will need about 106 phone lines. So that's the calculation and the argument that Erlang went through a long time ago. It's actually interesting that Erlang did this calculation before Markov chains were invented. In this video, we are going to calculate interesting quantities that have to do with the short-term behavior of Markov chains as opposed to those dealing with long-term steady-state behaviors. But first, let us introduce the notion of absorbing state. As indicated in this definition, an absorbing state is a recurrent state from which you cannot escape once you get to it. The transition probability from k to k is 1. So in some sense, you get absorbed by the state. For example, consider this transition probability graph. States 4 and 5 are both absorbing states. Indeed, when you get to 4, you stay in 4, or when you get to 5, you stay in 5. State 1, 2, and 3 are transient states. So if the Markov chain initially started in 4, then it will stay in 4 forever. If it started in 5, it's going to stay in 5 forever. But what if the Markov chain started in either 1, 2, or 3? Eventually, after some moving around, you will either make that transition to state 4 and get absorbed by it, or you're going to do that transition and get to 5 and get absorbed by the state 5. So the question is, are you going to end up in 4 or are you going to end up in 5? Well, we don't know for sure. These correspond to random events. But can we say anything about their probabilities? Well, let us try to calculate the probability that you end up in 4 as an example. First, it seems plausible that this probability of ending in 4 will depend on where you started. If you start in 2, you probably have more chances of getting to 4 than if you started from 3. Because if you start from 2, at the next step you have immediately the chance of getting to 4. But if you start from 3, there is some chance that you will go to 5 and never go to 4. Or you will have to go through 2 in order to get to 4 anyway. So it looks like the probability of reaching 4 given you started from 2 will be bigger than if you started from 3. Now from 1 it's unclear. Let us be systematic then. Let us consider all possible probabilities to end up in 4 depending on the initial state. So let us ask this question. What is the probability A of I that the chain eventually settles in 4 given that it started in I? So in other words, A of I is the probability that you end up in 4 given that you started in I. Now the answer to that question is very easy for some cases. If you start in 4, the probability that you end up in 4 is 1. And if you start in 5, the probability that you end up in 4 is 0. There is no way that you can go from 5 to 4. What about the other cases? Well, it's not so clear. Let us consider, for example, that you started from 2. What could happen next? Well, from state 2, let's build a tree. You can either, with a probability 0.2, go to 4, or with a probability 0.8, you will go to 1. Now, in the first case, you're done. You reach 4. But in the second case, you arrive in 1. And what happened next? You don't know. But what you know is that from that state, either eventually you go and get trapped in 5, or you go and eventually get trapped in 4. What are the probabilities of these events? Well, we don't know. But one of them has been defined before. This represents the probability of ending up in 4 given that you start in 1. And that has been defined here. This is nothing else than A1. So the overall probability of interest for us, which is A of 2, using the total probability theorem, you can enumerate all options. It's with probability 0.2 you will go to 4, and then the probability of going to 4 given that you started in 4 is A4 plus 0.8 times A1. Now A of 4 is of course 1, as we have discussed before. So we get a relation between A2 and A of 1. Now of course you can do the same thing for the other state. For example, if you started from 1, what can happen next? Well, you can go to 2 with a probability 0.6. Once you're in 2, you are asking yourself what is the probability of reaching 4? Well, by definition it's A2. Or from 1 you go to 3 with a probability 0.4. And given that you have done that, what is the probability that eventually you reach 4? It's A3. If initially you start with A3, what can happen next? Again, with probability 0.3, you will end up in state 2, and there A of 2 is the probability of interest. Or with a probability 0.5, you go to state 1, and in that case you get A of 1. And finally, with a probability 0.2, you get trapped in 5. Right? You can write it if you want, but 0.2 and you get trapped in 5, but we know that A of 5 is 0, so this term will disappear. So in the end, you get a system here, after you replace A4 by 1 and A5 by 0, you get a system of 3 linear equations with 3 unknown. And it is easy to solve. I will not do that, you can do it yourself, but here are the results. You will get A of 1 equals 18 over 28. A of 2 will be 20 over 28. And A of 3 will be 15 over 28. Now I expressed them so that we can compare them easily. And as a sanity check, you can verify that indeed the probability starting from 2 will be larger than the probability starting from 3. And it turns out that A of 1 will be in between the other two. So these probabilities are consistent with our previous intuitions. As an aside, note that you could have written a system of 5 linear equations with 5 unknown. The 5 unknown corresponding to the 5 states possible. In fact, we had our 5 equations here. Here was 1, another one here, and 1, 2, 3. So 3 plus 2, 5. Of course, this one was easy. It was A4 equals 1 and A5 equals 0 that you can replace then there, and you get a limited or restricted or smaller system of 3 equations with 3 unknown. Now, what if you had been interested instead in finding the probability B of I that the chain eventually settles in 5 given you started in I? How to do that? Well, you can repeat exactly all this calculation that we have done, but looking at 5 as the state of interest. But of course, you don't have to do this. For any state I, given that you started in I, you will eventually with probability 1 end up in either 4 or 5. So you have A of I plus B of I equals 1 for all possible I. So once you have calculated A1, A2, A3, A4 and A5, you get B1, B2, B3, B4 and B5 by using this formula. To sum up, in general, the calculation of the probabilities to reach a given absorbing state S, starting from any state I of a general Markov chain with M states, so let's assume that you have M states, will be the unique solution of a system of M equations with m unknown, with the additional conditions that a of s equals 1 and a of s prime equals 0 for the other absorbing state. Now, going back to the following question that we posed at the end of the review on steady-state behavior, we had this diagram and we wanted to know which recurrent class this chain would end up if it started in one of these transient states. Well, we can now answer this question. For the purpose of this calculation, the trick is simply to think of a recurrent class as one big absorbing state and go through the calculation as we have done here. So think about this class, for example, as being one big state, an absorbing state, and now forget about the inside and calculate the probability that you end up in this class as the probability of reaching this absorbing state, given that you started in 1, 2, and 4, and you do the same kind of calculation. In this video, let us look at a second quantity of interest that has to do with absorbing states. Now that we know how to calculate the probability of getting to a given absorbing state, we would like to know how long it would take to get to it. Let us first deal with that question when we have only one absorbing state. Let us consider the following Markov chain, which is a little simpler than the one that we had in the previous video. We have transient state, 1, 2, and 3 are transient state, and we have one recurrent state, 4, and that recurrent state 4 is an absorbing state because once you get to it, you stay there forever. So in this simple example, the absorption probability to 4 is trivially 1. No matter where you start, with probability 1 you're guaranteed that eventually you will reach 4. But the question of interest is to know how long would it take to get to 4. In other words, how many transitions will you have to do until you reach 4? Of course, we don't know. It is a random variable. In fact, it's more than one random variable. It will depend probably on where you started. Starting from 2, 1, or 3, or 4 would lead to different random variables. We are going to be interested in looking at their expectation, or the expected value of these random variables. More precisely, let us define exactly what we want to do, which is to find the expected number of transitions that we're going to call mu of I, until reaching 4, which is our absorbing state, given that the initial state is I, one of these 4 states. First, as a warm-up, let's do some quick calculation. If you didn't have this part here, and instead we were looking just at this portion here, and make this one disappear like this, and replace it by a loop of probability 0.8. So now if you start from state 2, with probability 0.2 you will go to 4, or with probability 0.8 you will remain in 2. And now you ask yourself, what is the number of trials you have to do until you reach 4? Well, we know what it is. This is a geometric random variable with the probability of success, which is a success being going to 4, of 0.2. So the expected number of trials starting from 2 that you will have to go through until you reach 4 will be 1 over this probability. So 1 over 0.2, which is 5. Now that we have done this quick calculation, it should be clear that if we go back to the previous Markov chain that we had here, the expected time mu2 would probably be bigger than 5. Since from 2, not only you have the probability of going to 4, but you might have some chance of traveling there. So probably the number of time until you reach 4 will be bigger than 5. Let us see. Well, first of all, if you start at 4, the expected number of transition until reaching 4 will obviously be 0. So here, for I equals 4, you indeed get 0. What about for the others? Well, again, this is what we would like to calculate. How are we going to do that? Well, the argument is going to be of the same nature as the one that we used before. We are going to think in terms of tree and consider possible options starting from a given state. So let's do this calculation from 2. So you are 2, and we're going to build that tree here. So you are in state 2. What could happen next? Well, you can either transition to 4 with the probability 0.2, or with the probability 0.8, you end up in 1. And you have done one transition here, right? So plus one transition. So you are interested in calculating mu2. After one transition, you either end up in 4. In that case, you stop, you're done, right? In other words, the resulting value here would be mu4, which we know is 0. Or you are in 1. And now, given that you are in 1, you want to find the expected number of transition until reaching 4, which is exactly defined here. So here what you have is mu1. And now you can use the total expectation theorem to put all of these things together, which what it means is that mu2 will be 1. You have one transition, and then after you do that transition, with probability 0.2, you know that you're going to be in 4, and the expected value then will be mu4 plus 0.8, which is the probability that you end up in state 1, and condition on that, the remaining expected iterations until reaching 4 will be mu1. Now this one is of course 0, so what you end up is 1 plus 0.8 mu1. So you get a relation between mu2 and mu1. Now you can do the same thing if you start from 1 or start from 3. So let's do it again. From 1, so you're interested in 1. After one transition, so plus 1, what happened? Well, with the probability 0.6, you end up in 2. And with the probability 0.4, you end up in 3. And from 3, if you start in state 3, after one transition, what happened? Well, with the probability 0.5, you would end up in state 1. And then the expected number of transition from state 1 until reaching 4 will be mu1. Or with probability 0.5, you end up in 2. So again here, if you look at these three here, this is a system of three equations, three linear equations with three unknown, and it has a unique solution. I will let you do the calculation. Let me give you the result. What you obtain is mu1 will be 110 over 8, and the reason I'm writing it this way is so that we can compare them. Mu2 will be 96 over 8, which is 12, and mu3 is 111 over 8. So here again a quick sanity check. The number that we get here, 12, is indeed bigger than the 5 that we have obtained when we restricted ourselves to this set. So we do have mu2 greater than 5. Now, as the relative value between mu1, mu2, and mu3, it sort of makes sense. Mu2, the state 2, is the one closest to 4. It is the one actually linked to 4. So in some sense, the expected number of transition to reach 4 will always be the smallest one, because starting from the other states, you will have to go to 2 before going to 4. And in general, if you have a general Markov chain with transient states and one absorbing state, and you are asking yourself what is the expected time to absorption to that unique absorbing state, it will be the unique solution from the system of equation given here, where the Pij are the transition probabilities of your Markov chain. Now, we have seen how to solve this problem when we have one unique absorbing state. What happens if you have more than one absorbing state? Like, for example, in this case. Well, first of all, a quick note. you realize here that you have 1, 2, and 3 transient states, and indeed here you have 4 as an absorbing state. It's a recurrent state, and once you get to it, you stay there forever. And 5 is also a recurrent state, and once you get to 5, you stay there forever. Right? So 4 and 5 are both absorbing states. And in the previous video, we had seen how to calculate the probability of ending up in 4 as opposed to ending up in 5. What we know is that the probability of ending up in 4 plus the probability of ending up in 5 will be 1, but since the probability of ending up in 4 is not 1, trying to find the expected number of steps until you reach 4 specifically does not make much sense. That expectation, or that random variable, it's a random variable, but that expectation will be infinity. Why? Because there is a positive probability that you will end up in 5, and if you end up in 5, once you get there, the number of steps to go to 4 will be infinity. So it makes more sense to think about what is the expected time to any absorbing state, so to either 4 or 5. Now, if you are interested in that quantity, one trick in order to solve that problem using the technique that we have seen so far is to combine 4 and 5 into one mega state, call it whatever, 6. Right? And 6 is a combination of 4 and 5. It's a big absorbing state. And once you're in 6, you stay in 6. Right? And now you just have to define exactly what is the probability of transition from 1, 2, and 3 to that mega state. Well, here from 2, you had originally 2 arcs. You're going to combine these 2 into one arc. And you're going to sum this probability. So you had 0.3 and 0.2. You put on here 0.5, and on this arc you had only one arc, so you maintain that arc, and you have that probability that you had, which was, I believe, 0.2. Now you go back, if you look at the situation now, it's very close to the one that we had here. Right? So this 4 that you have here is this 6. Now, of course, you have another arc here like that, but that's fine. You can still add the arc here and put it as 0.2, and then you reduce this one to 0.3 to make it coherent here. But the idea on how to solve that is identical to this one. You would have to change a little bit of this, but this is the same technique. So in the end, we have seen a technique to find the expected time to absorptions whenever you have absorbing states in a given Markov chain. In this video, we continue our exploration of quantities of interest associated with the short-term behavior of Markov chain. This time, we suppose that we have a Markov chain composed of a single recurrent class, such as this one. Here we have our recurrent class, and these are transient states. We also assume that we are interested in a specific recurrent state, let's say 9, so this is my state S, and we will assume that the Markov chains start from a given initial state, state I, and assume that I is 1. Now the question we ask is, given that you started in 1, how long is it going to take to reach 9 for the first time? We know this is a recurrent class, so we know that the Markov chain eventually will come to that class and circulate here. So you know that the Markov chain will get to that state, 9. You are interested in knowing when it does so for the first time. Of course, we don't know for sure. This is random. It is a random variable, and let's try to calculate the expected value of this random variable. So more precisely, this is what we would like to do. We would like to find the mean first passage time from I to S from any starting state I. Here we're going to illustrate that with 1. And mathematically, this is what we have here. So here again, what you have is that the Markov chain started in state I at time 0. And now you are looking at this set here. And this set records all the time n, such that your Markov chain xn is in the state S of interest. So out of this set, you are looking at the minimum n that verifies that. So this is going to be a random variable, and you take the expected value of that. And this is what we call the mean first passage time from I to S. Again, this is the expected number of steps in order to get from I to S for the first time. So how do we go about calculating such a quantity? Well, let us think a little bit. We are looking at the event that you will visit 9 from 1 for the first time. What happened after visiting 9 is of no relevance in our calculation. In other words, our calculation will never involve this arc and will not involve this arc either, because in order for the Markov chain to traverse this arc or this one, it would have to visit 9 first. So what it means is that we can forget about this arc and we can forget about this arc, in a sense that they don't matter in the calculation of the mean first passage time to S. Now, removing these arcs entirely means that you would have to increase the probability of that self-transition from 0 to 1. So what do you get? Well, you get this following graph. We have removed these arcs and we have increased the probability 0.2 here to 1. And again, we have argued that calculating the mean first passage time from I to S in this graph is the same as doing the same thing for this graph. But here we have a very special structure. We have only one recurrent state left, which is state 9, and that state is an absorbing state. All the other state, this one was transient, 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 this one become a transient state, and this one is also a transient state in this new transition probability diagram. So we get a situation where we have one single absorbing state, and we are interested in calculating the probability starting from I to reach that absorbing state, and also the number of steps it takes to do that, which is what we did in the previous video. So let us repeat what we had seen before. So this is going to be the unique solution to this system. T of S equals 0, of course. Since you start from S, you are in S, and so the amount of time it takes to get to S is 0. And otherwise, for all the other states that are not S, this is the resulting system of equation that we have. And the unique solution of this system gives you the result of finding the expected amount of time to go to the absorbing state S. So using this simple trick, we have been able to use the previous calculation to calculate something else. Let us consider a related question, which we call the mean recurrence time of S. Here, let's go back to the original graph, and this is our state S. And now the question is the following. Given that you are in S, what is the amount of time it will take for the Markov chain to return to S for the first time? So for this question, the Markov chain is currently in 9, and you ask yourself, how long is it going to take once you leave 9 to return to 9? Here again, we don't know for sure. It's a random variable, and we are interested in the expectation of that random variable. In other words, in the expected number of steps it takes in order to get back to 9 once you are in 9. And this is what we mean by the mean recurrence time of S. And mathematically, this is what it is. It is almost the same formula as the one that you had here, except that here you have n greater than or equals to 1 as opposed to n greater than or equals to 0. It simply means that you're not interested in the first time that you are in S because you start from S. So you want to have n greater than or equals to 1. n equals 0 would not work. Ts of star would have been 0. So how would you solve that problem? Well, here again, you use the same trick that we used before and think in terms of tree. Let's look at the Markov chain in state 9. What can happen next? From 9, it can go to 3, or it can go to 5, or it can jump on itself. So this is with the probability 0.2, this is with the probability 0.2, and this is with the probability of 0.6. And now after you make one transition, so that you are in 3 now, what is the time to get to 9? Well, it's exactly T3, where the T is the solution here of that previous system. What about from 5? T5. And what about from 9? Well, T9, and T9 was 0. So from that tree, what you have is T9 star will be 0.2 times T3 plus 0.6 times T5 plus 0.2 times T9 plus, of course, 1 because you have done one transition. Where again, this value of T3, T5, and T9 are the one corresponding to this solution here. So of course T9 is 0. So what we have shown here that in general, this is actually what you would have, and this is exactly what we have written here. Ts of star is 1 plus the summation of Psj of T of j, where T of j is the solution to this system. So again, you started from 9, you have to do a transition first. You can do a transition onto yourself, you can go to 3, or you can go to 6. After that transition, which counts for the number 1 here, what happened is you are trying to find the solution to this system, which is the mean first passage time from the current state where you are to 9. And then when you put these two things together, you get the mean recurrence time of 9. In this last video, we illustrate how to use the techniques we have recently learned in order to answer some questions about the following classical problem. Consider a gambler putting a bet of $1 in a game that has a payoff of $1 if she wins. We assume that this is a fair game, so that the probability of winning $1 on each play of the game is 1/2, and so the probability of losing the bet is also 1/2. Suppose that she starts with high dollars and continues to play the game until either she reaches a goal of $n or she has no money left, whatever comes first. Let us consider a first question, which is the following. What is the probability that she ends up with having her goal of $n? Now, how to go about solving this problem? Can we think of a Markov chain representation for this problem? But in that case, what would be good choices for the definition of the states? Let us think. At any point in time, the only relevant information is the amount of money the gambler has available. How she got to that amount in the past is irrelevant. And if this amount is neither 0 nor n, then she will play again, and the next state will be a number which will be increased or decreased by 1 unit, depending on winning or losing the next bet. So we can represent the possible evolution of this game with the following probability transition graph. So we have n plus 1 states. This is the state where she loses all her money. This is the state where she has high amount of money before the next betting. And here this is the state n where she reaches her goal and she can leave. In terms of the transition probability, assuming that you are at a given time in that state, that means that you have high money in your pocket, and you play the next bet, with a probability 1/2, you will gain or win, and so your amount of money is I plus 1, or you lose and your money is I minus 1, and you keep repeating until you reach either n or 0, and then you stop. So this is a Markov chain, and that state 0 and that state n are absorbing states. Once you reach them, you stay there forever. So what this question is asking is the probability A of I of starting from I, what is the probability that you will end up in that absorbing state? And we have done this calculation previously. So let us repeat the technique very briefly. Clearly here, if you start with $0, you will never reach that, so it's going to be 0. On the other hand, if you start with your desired goal, you don't play anymore, so your probability is 1. Now, of course, what is of interest is if I is strictly between 0 and n, and now the question is how to calculate that probability. And we have seen that the way to do that is to look at the situation and say, well, let's assume that you are in that state I, and what will happen next? Well, with a probability 0.5, you will move to that state, and now you are in that level with I plus 1 amount of money. And what is the probability that, given that you are here, you're going to end up in n? It's going to be AI plus 1. So it's AI plus 1. Plus, the other alternative is that you are going to lose money and end up in that state. And there, the remaining probability to reach the time n is AI minus 1. So you have this kind of equation. This is valid for all I between 0 and n. And this is a system of equation that you can solve. It's not very difficult to solve. Actually, you can look in the textbook. There will be some trick to do that. There are many, many ways to do that. We're not going to spend our time going that in details, but essentially if you solve that system, you will see that the answer will be that A of I is I over n. So if you start with I amount of money, the probability that you're going to reach your goal n here is I over n. So here clearly, if you're extremely greedy and you have a very, very, very high goal, that means n is very, very large, so large that compared to your initial amount I, n can be considered to be infinity. Then the probability that you're going to reach your high goal will go to 0, where n goes to infinity. So again, if you're extremely greedy, no matter how much your fixed amount of initial money is, the probability that you will stop the game reaching your goal is going to be increasingly small. And since the other state is 1 minus this one, the probability that you're going to get ruined is going to be closer to 1. All right, so we have that answer here. What about the next question? Next question is the following. What would be the expected wealth at the end? Again, this is a Markov chain where there are two absorbing states. All the others are transient. You're guaranteed with probability 1 that you will reach either 0 or n. So it's a valid question to know, once you reach either 0 or n, what is the expected wealth at the end? Well, it's going to be, if you arrive here, it's going to be 0, and if you arrive here, it's going to be n. So the expected value of that wealth will be 0 times the probability of finding in that, plus n times the probability of getting there. So it's going to be that expression, 0 times 1 minus A of I, plus n times A of I. And here what we then get is n times I over n, which is I. Which is quite interesting. This is exactly how you started. So in some sense, in expectation, there is no free lunch here. The next question is, how long does the gambler expect to stay in the game? We know that eventually you will either reach 0 or n with probability 1. The question is, how long is it going to take? And again, we have seen in a previous video that this is essentially calculating the expectation to absorption. And we know how to do that. So let's recap what we had said. If you define mu of I to be the expected number of plays starting from I, what do you have? Well, for I equals 0 or I equals n, either way, if you start from here or you start from here, the expected number of play is 0, right? Because you're done. And otherwise, you use the same kind of derivation that we had. If you start at I between 1 and n, then you will see that mu of I, after one transition, plus 1, you will either be in state I plus 1, and in that case, this expectation will be mu I plus 1, or you will be in state I minus 1, and in that case, the expectation is mu I minus 1. So this is an equation that you have, which is almost the same as this one, except that you have a plus 1 in it. And as we had discussed before, in general, this is the kind of formula that you have. Now, you can solve this system I will let you do that. There are many ways to do this, but the solution that you're going to have is that mu I will be equals to I times n minus I. This is the result. Finally, what would be the case if you didn't have a fair game? For example, unfair to the gambler or unfair to the casino. So what we mean here is that the probability P is different from 0.5. So here instead of 0.5 you have P everywhere. And here of course you have 1 minus P everywhere on this side. So you have a probability P of winning and probability 1 minus P of losing each bet. So you might ask the same question. Well, for the probability A of I, you still have 0 here, you still have 1 here. The formula that you would write here, instead of writing it this way, it would be, you start from here with the probability P, you end up here, and with the probability 1 minus P, you end up there. And the expression that you get for A of I, if you define R to be 1 minus P over P, you will see that A of I is going to be 1 minus R at the power I over 1 minus R at the power n. And what would be the expected amount of time she will play? Instead of that equation, if you solve it, you would have mu of I equals R plus 1 divided by R minus 1 times I minus n times 1 minus R at the power I divided by 1 minus R at the power n. Because you would have here again P and 1 minus P here. And you can see that when P is strictly less than 1/2, in other words, it's even worse for this gambler, then A of I, which is the probability of getting to this favorable state, will also go to 0 when n goes to infinity. And in a case where P is strictly greater than 0.5, that means that she has some favored odd on her favor, then in that case this number R at the power n will go to 0, and 1 minus R of I will represent the probability that she would become infinitely rich. In other words, by being very greedy and going to infinity, this will go to 0, and 1 minus R at the power I is the probability that she would get infinitely rich.